everyone, and welcome to today's Explainer. We are about to unpack a literally transformative framework in educational psychology. Today, we're diving into the groundbreaking work of American cognitive psychologist Jerome Bruner and looking at how his theories completely revolutionize the way we understand learning, especially when it comes to math. We're going to explore exactly what his learning theory actually is, see it in action with some truly fascinating examples, and then discover how it forms the absolute bedrock of the highly successful CPA method that top math programs all over the world use today. I want to kick things off with this incredibly empowering quote from Bruner himself. Just take a second to really absorb this. Any subject can be taught effectively in some intellectually honest form to any child at any stage of development. I mean, wow. Bruner firmly believed that we shouldn't hold back complex ideas from young minds. If a kid is struggling, it's not because they lack the brain power. It's just because the information isn't being presented in the right way for them. With the right tools, young kids can absolutely master some seriously complex stuff. Which, brings me to a question I think a lot of us can relate to. Be honest, were you ever told, or did you ever just feel deep down that you just weren't a math person? If just hearing the word algebra gives you a little spike of anxiety, you are definitely not alone. So many of us grew up experiencing math as just this frustrating wall of rules. Rules we had to memorize without ever actually understanding why they worked. Well, this explainer is basically the antidote to that universal struggle. We're going to look at the exact psychological mechanism that ensures nobody gets left behind. Okay, let's dive into this. Here's our roadmap. We'll cover Bruner's cognitive learning theory, his 3 modes of representation, discovery learning in math, the CPA approach, how Bruner links to CPA, and finally, deep mathematical understanding. Starting off with Section 1, Bruner's cognitive learning theory, the constructivist mindset. Our journey starts at Harvard University. By shifting education away from strict rote memorization, Bruner put human cognition right at the center of learning. Central to all of this is the constructivist approach. Now, in this model, learning isn't just passively sitting there absorbing facts from a textbook or a lecture. No way. Instead, learners actively construct meaning for themselves. Bruner realized we are constantly organizing what we know based on new experiences. So, a teacher's job isn't just to hand out the answers, it's to facilitate discovery. It's about giving students the tools and asking the right questions so they piece the puzzle together themselves. To support this, Bruner came up with this brilliant concept called the spiral curriculum. Think of learning not as a straight line you just walk down once, but more like a spiral staircase. You revisit the same topics, like geometry or algebra, over time, but with each pass, you're looking at it with increasing depth and complexity. You're bringing your old knowledge up to a slightly higher vantage point. It's just an incredibly natural way for the brain to build robust, lasting knowledge. Moving right along to Section 2, 3 modes of representation from action to abstraction. So how do we actually encode the world into our memory? Bruner said there are 3 ways. First is the inactive mode. This usually dominates when we're babies, from ages 0 to 1. It's totally action-based. You learn by doing, by touching and manipulating physical objects. Second is the iconic mode, which peaks from ages 1 to 6. This is image-based. You start using visual images and pictures to understand things. And third is the symbolic mode, from age 7 onward. This is where you use abstract codes, like language or math symbols, to represent concepts. But here's the kicker. These don't just disappear as we grow up. They stick around and work seamlessly together for our entire lives. All right, Section 3, discovery learning in math, theory in action. Let's actually look at how this works with some real math. Bruner, along with his collaborator Z.P. Deans, ran an experiment to teach 8-year-olds the factorization of quadratic equations. Yes, you heard that right, stuff most of us sweated over in junior high, taught to 8-year-olds. How? Well, they handed them physical wood chips. A big square for x squared, a rectangle for x, and a little square for 1. This plunged the kids straight into that inactive mode. They could literally touch the variables. Then, the teacher just asked a really simple question. Can you use these pieces to make a larger square? The kids didn't write a single thing down. They just played with the wood chips. Through totally hands-on trial and error, they figured out how to fit the pieces together to form perfect, larger squares. They were actively constructing their own knowledge through physical action. It's literally like solving a puzzle. And then came the magic aha moment. The teacher asked them to describe what they built. First, they counted the parts. So 1 x squared piece, 2 x pieces, and 1 1 piece. Then they looked at the side lengths of the new big square, which was x plus 1 by x plus 1. By equating those two different ways of describing the exact same physical shape, these kids independently discovered the formula. X squared plus 2x plus 1 equals x plus 1 times x plus 1. They transitioned flawlessly from inactive doing right into symbolic abstract algebra. Now, this isn't just for algebra. Let's look at a geometry example to see this discovery method in action, finding the area of a circle. If you just give a kid the formula pi r squared, well, it's just a random rule to memorize. But if you hand them a paper circle and tell them to cut it into 4 equal pizza slices and arrange them, it kind of looks like a bumpy parallelogram. Cut it into 8 slices, the bumps get smaller, and it looks even more like a parallelogram. As they keep dividing that circle into more and more slices and laying them out, they visually see the shape turning into a nearly perfect rectangle. The width is the radius, r, and the length is half the circumference, pi times r. It is amazing to see how this iconic visual representation bridges the gap. They independently deduce the abstract symbolic formula for themselves. And because they discovered it, they own that knowledge for sure. Section 4, the CPA approach explained. Modern math mastery. This exact progression, from the physical to the visual to the abstract, is now the standard instructional framework used in the best math programs globally. Which brings us to Section 5, linking Bruner to CPA, bridging the gap. Let's connect the dots between the historical theory and today's classrooms. So here is the crucial point. It's a direct translation. Bruner's inactive mode, the action-based doing, is exactly what modern teachers call the concrete stage, using physical blocks or chips. Bruner's iconic mode, the visual seeing, is the pictorial stage, where students draw diagrams. And Bruner's symbolic mode, the language and codes, is the abstract stage, where we use actual numbers and math symbols. The CPA approach isn't some new fad. It is literally Bruner's cognitive blueprint in action. And finally, Section 6, deep mathematical understanding. Let's talk about why this actually matters for students. When schools use this CPA system, they are moving kids away from just memorizing empty rules. Instead, they're building a deep relational understanding where students know exactly what to do and why it works. It completely prioritizes depth over speed. Plus, if a student gets stuck on an abstract equation, the teacher can beautifully scaffold the learning by just stepping back to a drawing or the physical blocks to rebuild that mental connection. It creates this wonderfully inclusive environment where literally every learner can succeed. Bruner showed us that the human mind is uniquely built to understand the world as long as we're given the right tools to represent it. By grounding learning in that concrete, pictorial, abstract sequence, we're not just teaching math, we're teaching students how to think flexibly. So I want to leave you with this final thought. If this method works so incredibly well for things like quadratic equations and geometry, how might education completely transform if we applied the CPA approach to every single subject we learn? Think about it. Thanks for hanging out with me on this explainer, and keep actively constructing that knowledge.